We're talking about bootstrapping the blockchain. This is joint work with Aggelos Kiayas from Edinburgh and Athens and Yukon, Nikos Ioannidis from Athens, and Yorgos Panagiotakos, also from Athens. Okay, so I'll start with a brief introduction, and then we'll get to the intuition of the new protocol. So blockchain has to do with decentralized payment systems. And you know that in early mid-90s, there were these, systems proposed by Schaum and follow-ups on, eCash, DigiCash, and so forth, giving strong privacy guarantees, but, it was a centralized approach. So Bitcoin is the first decentralized cryptocurrency proposed by Nakamoto, and that means there are no national banks, mints, no deposit insurance coverage, and it's based on maintaining a public transaction ledger in a distributed manner. So January 2009, the network takes off, and there are a myriad of other cryptocurrencies following. And this thing has had a high impact, not just in the cryptocurrency space, but other applications such as contracts, reputation systems, name services, consensus, etc. Okay, so let me remind you briefly what the participants are. We're going to be going down to the backbone of the Bitcoin protocol, but we'll do some higher level application introduction. So remember what the players are. There's miners, payers, and payees. Miners are the parties who maintain the transaction ledger. They do work, and we're going to see what doing work means. And they get rewards for mining. Okay, that's the new Bitcoins, and they also get fees for transactions they install. Payers, they broadcast the transaction, stating that they send Bitcoin to other parties. And they rely on the security of digital signatures. I'm going to see it next, to ensure that these Bitcoins are not lost or stolen. Payees, the recipients of these transactions, have to generate a Bitcoin address account, and they have to verify that their account is eventually credited. Okay? Just quickly on the basic crypto that Bitcoin runs on. It's on elliptic curves, that curve. An account is basically a pair of keys, public key, private key. And the account is a Bitcoin address, which is a hash of the public key. That's an example. And the private key is used to sign on outgoing transactions. Okay, and there's some other object called wallet where all you store your private public key pairs. Okay, and the transaction is something like this. For example, this pseudonym, this public key with the pseudonym of, say, Yuval, is going to pay me some Bitcoin from some transaction. Okay, and this is signed using his private key, signing key. All right, so that's a transaction. The transaction have to be valid. And they are organized in something called a transaction ledger, TAO. And there's a well-defined predicate that determines whether a transaction is valid or not, if it makes sense. And each miner will accept it receives a transaction. We're going to see how. It's going to try to install it, depending on its local view of the ledger. Okay, so this is a payment system. So what's the litmus test for any payment system? Is that the payer should not be able to do this with the same coin. Okay, so that means that if one transaction is valid, the other one should not. Okay, and no honest miner will accept transaction. And as long as the miners agree on the state of the system, then the system is TAO, this ledger, then double spending is infeasible. All right. Now, if there was a single miner, then there should be no problem. Centralize everything, all the information, transactions, and figuring out which one is consistent or not. But then it's a centralized system. So the big question is what that Bitcoin addresses is how to facilitate multiple miners, okay, while preventing double spending, and moreover, how to do this, extended to thousands, lots of users at the global scale. In this type of system, which started to be called permissionless. Okay, and what is this permissionless system? It's not a traditional distributed system where parties know each other and they are authenticated, and you can think of real system as POWS running, or BFT, which stands for Byzantine fault tolerant, and more generally MPC, secure multi-party computation. Instead, this is a Newsweek cover. In this type of system, parties do not know each other, not even how many there are. Parties is dynamic, so parties come and go, and anyone can join. Okay, so we call it this unauthenticated system, but this is a name that is starting to catch up. Okay, so this is such a system, and in fact, we knew that for this type of system, there are strong impossibility results. Okay, and I'll get back to these soon, but one is by Okun back in 2005, and one in the MPC space by Barak, Kennedy, Lindell, Paz, and Rabin. That says, there isn't much you can do in this type of system. We will see what are the exact conditions under which you can do things. But anyway, there were strong suggestions you cannot do anything. Moreover, in this type of system, there were indications that civil attacks are unavoidable. This is a paper by Du Sur back in 2002. And moreover, there is a 1/3 barrier in the number of misbehaving parties. Okay, you have a network of n parties. So 1/3 was known to be the maximum that you can tolerate. And this is not only in the information theoretic setting, which is this reference that I have by Lamport et al., by a less known paper by Borcherding, which shows that even if you assume computational assumptions, like signature, you assume signatures, but there is no trusted setup, okay, you cannot go beyond 1/3. Okay, typically you would think in the computational setting you can do more than in the information theoretic setting, but implicitly that happens if you assume a PKI. And that's a trusted setup assumption. This is without any setup assumption, which would be the permissionless model. Okay, so what this? If you've read this, if you have read these papers, this why bother doing things? Well, except that Nakamoto comes in and says, well, you can do more, and you can use the blockchain based on proofs of work, also known as crypto puzzles, introduced by Dwork Naor. I'll read more on this later. And with a bunch of claims. In particular, it implements this Bitcoin system, implements a distributed public ledger assuming an honest majority, which is going to satisfy these properties, consistency and liveness. And moreover, he says, we're going to, the proof of work chain is also a solution to the Byzantine generals problem, okay, with an honest majority, which should contradict this bound. Okay? So let's look at this proofs of work a little bit more, also known as moderately hard functions, crypto puzzles. And they can be abstracted as follows by a polynomial time predicate that takes two arguments. One is a challenge, And the witness, one has to search for in a brute force way. And typically, you would assume a hardness, a complexity, a lower bound on the complexity of this search. Okay, and importantly, verification has to be easy. Okay, so that's the abstracted formulation of a proof of work. So how does the blockchain protocol uses proofs of work? Well, miners would collect 0 transactions. So the transaction could be that transaction that I mentioned where Yuval was paying me 1 Bitcoin. I'm getting back to you, Yuval, now, soon. Okay, and then they do work. Here's a pseudocode version of what they would do. Okay, so they have a hash version of the ledger. They include the transaction, the new transaction they have received, and this will be the witness that with which they search for a solution to this puzzle. And the puzzle is find something whose image is below this value. Okay, this is called the difficulty level of the puzzle. Okay, this is typically done using SHA-256, and notice that the leading zeros here, so it's not a 2 to a 256 output, but it has to be in a smaller range. All right, and if this while loop terminates, meaning that this miner doing this work has solved this puzzle, so he's going to broadcast the new block, which is a condensed version of the state, the witness and the new transactions. And I said broadcast in quotes because it's not really broadcast, but some other primitive that makes these things work. Okay, so what happens if you are a receiving party? You receive this new block, you check that you are on the same page, you verify the puzzle, and if so, if these things match, you extend the ledger by adding a block to the ledger. Okay, so this blockchain is essentially the sequence of, you can think of this sequence of triples. Okay. And it turns out that size matters in the sense that the longest chain wins, in the sense that if you are a miner, you receive something, you compare the difficulty of your own chain with the chain you have received, and only adopt it if it's bigger, longer than yours. Okay, which is what I say here. And this could happen, for example, here. This could be the transaction where Yuval was paying me 1 Bitcoin. I don't know how well you know Yuval, but he might change his mind. Okay, so he wants to erase a transaction, and able to do that, so he has to find a longer chain where his transaction doesn't appear. Okay, but in order to do that, he has to solve this proofs of work, right? And this setting, Nakamoto claimed, well, you need a majority hashing power to be able to do that. All right. So, so that was let me tell you our starting point, which is this paper we had called the Bitcoin Backbone Protocol in last year. And the motivation was our motivation was to try to do a more formal study of the blockchain protocol, perhaps a little bit more idealized, but there was a little analysis, and this is what happened around that time when we started. So our questions was, well, let's provide some somewhat idealized but also realistic modeling of this thing. What properties you can prove about this protocol, in what sense it implements a robust ledger, and Nakamoto mentions, based on the agreement, it seems to be contradicting the known bounds. So what's going on? Okay, so that's what we did. We analyzed Bitcoin in a general cryptographic adversary model. And we try to describe and extract the core, the foundation of the Bitcoin protocol. That's what we call the Bitcoin backbone. Okay, and in fact, we said, well, forget about the backbone application, we can parameterize every application by some basic functions, such as a validation predicate. We talk about transactions have to be valid. Okay, for Bitcoin, there's some way where inputs would make sense and some way to produce output from the blockchain. Okay, so we have those functions, and now we look at the underlying protocol. Okay, and this is what we show. We formulate two fundamental properties of this Bitcoin backbone, assuming a half-bounded adversary and high network synchrony, which we call common prefix and chain quality. Common prefix says, well, parties are building their chains, okay, but if you prune, the head of the chains enough, they run, for a long enough, then you're able to prune, from the top. Then the prefix should be common, and that's the idea of agreement. You have to agree on this distributed ledger object. And the chain quality captures the fact that now, if you are an honest miner trying to insert transactions, you should be able to get through. Okay, there are a lot of potentially malicious mining doing things, or mining for their own sake and stuff. But the parties who follow the protocol should be able to get through and getting transactions installed. Okay, so we can formulate these abstract properties of this data structure, and from that captures if Bitcoin works and if consensus or Byzantine generals work. Okay, so this is a sort of a idea of what would happen. The miners would be mining. They might diverge at the head of the chains, but if you prune, then there should be a common prefix. Okay, and we showed that from these properties you can solve Byzantine agreement and the public ledger. This is the Bitcoin application, assuming this bound on the hashing power of the adversary. Okay, essentially we can do, if you look at the end, for a half-bounded adversary, we can show that the Bitcoin application will work and the Byzantine agreement would work. Okay, so we needed a model for this. In this version, we said that the permissionless model is dynamic. Parties come and go. So for this analysis, we assume a fixed number of parties. I'll come back to the dynamic setting later. About the communication graph, it's not what we are used to, this point-to-point network, but it has this TCP/IP-like primitive that we call it here ABC for anonymous broadcast, where parties cannot authenticate each other. In fact, the adversary can spoof the source of the message, and this is what was considered in these works that I mentioned, but it cannot disconnect honest parties. Okay, not only cannot be disconnected, but if an honest party broadcasts, all other honest parties are going to get what he broadcasts. Okay, and it's anonymous, pseudonymous, because you don't know where it's coming from. Then you're going to check the payload, see if things work out and so forth, but you get the broadcast. Okay, so we call that ABC. And I said somewhat realistic because for this analysis we assume that the system is synchronous. So there is some notion of round, okay, where parties send messages, receive messages, and then do some computation. They don't have to be lockstep. For simplicity, we assume that it's lockstep. Okay, but the important thing about rounds is that we want to be able to compare the distribution of information versus the ability to generate proofs of work. Okay. So, and moreover, we work in the random oracle model. And we assume, say, Q, parameter Q, number of queries to random oracle per round. Okay, we assume that T of the parties are controlled by the adversary, means that the aggregate number of queries would be that, and then this bound corresponds to minority of hashing power. As Bobby says, importantly, here's the trusted setup assumption. that there is an unpredictable genesis block. Okay, so all chains have to start from the same block, which is supposed to be unpredictable, and this was the stuff that is embedded in the Bitcoin code. So it's an article by the Times from that date. Okay, so that's a trusted setup assumption. Everybody started mining, trying to solve proofs of work based on this genesis block. All right, so this is what we do in this work. Get rid of this assumption, and we're going to let parties, pretty much in this model, build their own unpredictable genesis block. And that's why we call this we have the Bitcoin backbone. This will be the Bootstrapped Bitcoin backbone. And so this is something that recent addition, so I'm not sure that checks out. But I figured it would be interesting to contrast what's known and what's achievable in this new model. Okay, let me answer. So here I call it the consensus taxonomy. Some of the results are for Bitcoin, but let's call it consensus anyway. Remember what the consensus problem was. There is an agreement property. Everybody starts with a value agreement. Everybody has to agree. And validity means it's all starting with the same value. That has to be the output. Okay? So this is what we came up with in terms of models. So notice that we have something that we call the network assumptions or resources that you have access to. This layer will be the computational assumptions. And here will be if you assume setup or not. Okay? And this is, so in the network layer, we can be synchronous or asynchronous. Okay? So let's, this asynchronous branch is pretty much what we know, what the UC model would fall. Okay, where there's no limit. The adversary has control on the network and can block delivery of messages forever. Okay, as opposed to the distributed computing version of this model, which we call with asynchronous with eventual delivery. And that was, you might remember the basic lower bound by Fisher, Lynch, and Patterson. That says that, deterministically you cannot do anything in this model. But here the difference between the two is that the adversary can delay arbitrarily but cannot prevent the delivery of the message, except that an honest party cannot figure out whether it's waiting, that the message is not coming from a good guy or from a, that is late or a corrupt party. Okay, and here's the synchronous branch, which is more populated. So let's look at this. So let me just say, because I don't have much time, that there isn't much. Here we are pretty much doomed, right? And if you're talking about Bitcoin applications, if you're trying to have some idea of proofs of work in a certain time, then here they don't seem to be very meaningless. This is less known, but in the synchronous world, call it synchronous or semi-synchronous or partially synchronous, where there will be a known bound in the delivery of messages. I call that synchronous here. So here you can split in the network layer between point-to-point and this primitive that I call ABC, anonymous broadcast. So these are pretty much known results. Okay, the things that you can do, assuming one-way functions or an information theoretic setting. And this is assuming, trusted setup like a PKI and now trusted setup and conditional, you don't have anything. Well, you have other type of setup in the unconditional setting. But this is the new setting, okay, where we are in the anonymous broadcast network model. And here we have unconditional, of which we don't know also much what's going on, what can be done. But in this world where you use proofs of work, as I described, okay, you can do, assuming setup, we can do the protocol that I just mentioned. Okay, this Bitcoin backbone protocol and this more recent protocol, POWS, Shellet, and another S. Okay, and here you can tolerate up to less than half of a corruption. And in the no setup world, Okay, this is what we are. Okay, and this was also achieved last crypto by Andrikovsky and Zimbowski, okay, but in a more indirect way. So we show how to do this in a seamless blockchain type way. Okay, so no trusted setup, meaning that there's no starting point for everybody. So parties are going to be able to pre-compute. Okay, so you have to take care of that. You have to model that in a suitable way. And there's a way of modeling that following one of Canetti's models, except that here you also want to make sure that the party has enough steps to do the queries in each round. Okay, so but this can be modeled. And this is what we do. Okay, so we have this absolute hashing power, and we go from trusted setup to no trusted setup. And here I make a distinction between one-way functions and proofs of work. Okay, in the taxonomy I wasn't. Okay, and it's seamless integration with the backbone protocol. Okay, and there's been related work in the sense of using proofs of work to generate the trusted setup object, and that was, to my knowledge, first done by Aspnes et al. That's Sybil, in case you didn't know her, to prevent Sybil attacks. Okay, so essentially in an anonymous system, he suggested let's do proofs of work so that parties get identity proportional to their computational power. And there's been some other work. So the problem with this is that the PKI was not consistent. These guys, Katz et al. And Zimbowski et al. Show how to set up a consistent PKI, also no trusted setup. But here the thing is you have to do a trusted setup, okay, a PKI, and then you would run classical protocols that you know to do consensus agreement or whatever. So that's not what we do here. We do not set up PKI. And so the new protocol looks like this. There are two phases. The first phase where the parties exchange challenges, that would be the randomness that goes into the Genesis block. And then they would use the basic backbone functions. And basically other differences are that now you're going to end up with a bunch of candidate Genesis blocks. So when you validate things that are coming in, you have to take care of this possibility. And also before, we just look at the length. Okay, here we're going to be ranking Genesis blocks according to some rules. Okay, but the structure of the protocol will be like this. So the system start, okay, and the adversary can get started earlier. Okay, can do some pre-computation, whatever he wants, subject to our model, as I mentioned. And then at some point, the honest parties get activated, and here's where the protocol start. Okay, and then you have the phase where the exchange challenges, and then they start mining. I mentioned this, having to figure out what's the right Genesis block and so forth. And then after a while, they continue mining as before. Okay, I don't have time for this, but this would be the exchange phase, the mining and the Genesis update, and then how they continue with the mining. So I have like 30 seconds. So the rank, here, as I said, Genesis blocks are ranked according to some function. Okay, they don't have the same value, so there is some uncertainty, and I don't have time to do this. But essentially, the problem was when you are generating proofs of work, in order for the adversary to be able to make you diverge, has to be able to generate a proof of work for each time that one honest guy generates a proof of work, right? In this case, in our case, was relatively easier, okay? But here, things are more complex because you have to be able to, counteract, you do some matching between the proofs of work that everybody is generating and the proofs of work generated by the honest parties, and there's much more uncertainty. Okay, so David is getting nervous. So this is what we achieved. Okay, we got rid of the unpredictable Genesis block assumption for this Bitcoin backbone protocol. Interestingly, you would like to, I mentioned this proof of work in an abstract way. It would be nice to have a clean complexity theoretic characterization of these subjects. Also, a simulation-based treatment of blockchain protocols, because people are talking about we do this blockchain and then we mix it with some other protocol. So this composition aspect is not clear how it would work out. And finally, I mentioned about fixed number of parties. Okay, and what you like to do is have the real Bitcoin system where parties come and go, and as that happens, the difficulty level changes according to the code. Okay, but that has to be, that's something that we've been analyzing. It looks like we can show under what conditions this works. Okay, sorry for the delay. Thank you.